Here is another example about shear stress to our current topic, simple stress. The members of the structure in the figure weigh 2,920 Newton per meter. Determine the smallest diameter of pin that can be used at point A if shearing stress is limited to 34.5 megapascal. Assume single shear. I have here some simple steps in order to solve for this problem. We identify first the shearing stress on the assembly, and for the second step, we solve for the force acting on each member of the structure. For the third step, we will solve for the force acting at the pin at point A, and for the fourth step, we will solve for the problem by applying the equation for shear stress. We will begin with step number 1. We identify the shearing stress on the assembly. The problem tells us to assume single shear. So the area is just equal to the area of pin at point A of the structure. Since it tells us about diameter, it means it is a circular area. So area is just equal to pi d squared all over 4. Then we move on step number 2. We solve for the forces acting on each of the member of the structure from the given weight of the members. So the weight of the members is just equal to 2,920 Newton per meters. That is uniformly distributed over the length of member AB and member BC of the assembly. So if we multiply the length of members into the intensity of the load, that is equal to 2,920 Newton per meter, we can find for the weight for member AB together with the weight of member BC. So we have to calculate first for the length of member AB and BC. Then we will multiply to the intensity of the load. So for member AB, length is just equal to 1.22 square. Then 1.20 plus 1.22 square, we take the square root. That is by Pythagorean theorem, it is equal to 1.72 meters. So weight for AB is just equal to the intensity multiplied by the length of member AB, that is equal to 5,034.69 Newton, and it is acting mid-length of member AB that is located 1.22 divided by 2 from point A, and that is also 1.22 over 2 from point B of the assembly. For member BC, length of member BC is just equal to 1.83 square plus 0.91 square. We take the square root, that is also by Pythagorean theorem, that is equal to 2.0 meters. For weight of member BC, which is located also mid-length of member BC, that is equal to 2,920 Newton per meter multiplied by its length, that is equal to 5,970.41 Newton. After solving for the weight of members of the assembly, we can now solve for the force acting at point A of the assembly. We will apply here equations of static equilibrium. We will apply summation moment at point C of the assembly. Since that is a pin support, it will not resist moment at that point. So if we apply summation moment at point C, AY multiplied by its moment arm, that is equal to 2.13, is clockwise with respect to point C. We will assume that clockwise moment are positive, so this is positive. Then AX multiplied by its moment arm, that is equal to 0.61, is another clockwise moment with respect to point C, so that is also positive. Then 5,034.69, that is weight of member AB multiplied by its moment arm, that is equal to 1.52 with respect to point C, that is counterclockwise. It is negative in our equation. Then 5,970.41 multiplied by its moment arm, that is 0.46, is also counterclockwise with respect to point C. It is also negative from our equation. 1.52 meters is calculated from the equation equal to 1.22 over 2 plus 0.91 meters. And for 0.46, that is just equal to 0.91 divided by 2. So let this equation to be equation 1. Then we will apply again summation moment at point B. At this time, we will only consider the left part of this assembly as our free body diagram, or member AB as free body diagram. So here is now member AB. We will apply summation moment at point B. Since point B is also a pin connection, it will not resist moment at that point. So we will now apply summation moment at point B is equal to 0. So AY with respect to point B multiplied by its moment arm, that is equal to 1.22, is clockwise with respect to point B. Then AX multiplied by its moment arm, that is 1.22, is counterclockwise with respect to point B. So it is negative in our equation. Again, we assume here that clockwise moment are positive. Then 5,034.69 that is the weight of member AB multiplied by its moment arm, that is 0.61 or 1.22 divided by 2, that is counterclockwise with respect to point B. It is negative in our equation. So let this equation to be equation 2. If we simplify equation 1, we can find for this equation. So solving equation 1 and equation 2 simultaneously, we can solve for AY, which is equal to 4,355.73 Newton, and for AX, that is equal to 1,838.38 Newton. You can enter equation 1 and equation 2 into a powerful calculator, and using some techniques, we can solve immediately for the values of AY and AX. For the equivalent force acting at point A, that is just equal to square root of AX squared plus AY squared, or it can be calculated from this equation, that is equal to 4355.73 squared, that is AY, and AX, which is equal to 1838.38 squared. We take the square root, and that is equal to 4,727.79 Newton. And after solving for the force, we can now solve for the unknown by applying the formula and the given condition. So tau, that is symbol for shear stress, that is equal to force divided by area. So area is just equal to pi d squared all over 4. That is for single shear. That is equivalent to the area of a circle, since we talk about diameter. So P is just equal to the force applied, which is equal to 4,727.79 Newton. And tau is given in the problem, that is equal to 34.5 Newton per millimeter squared. So we can solve for the area from this equation, that is equal to force divided by tau, or the shear stress. We can equate the value of area with pi d squared all over 4 into force divided by the shear stress, and we can find for diameter d from this equation, that is equal to 13.2 millimeter. So I hope again that you have learned a lot from this example. To those who want a copy of this file in PDF, like and subscribe. Comment down your email below and I will send it to you. Thank you.